This is example 1.3-9. Find support reactions at A and B, and then use the method of joints to find all member forces. Let C equal 8 feet and P equal 20 kips. And so remember, kips are thousands of pounds. And if we look over at our structure over here, we can see that each bar or section, which we call a member, is a two-force member. So all the forces at the end of each end of the member combine into a single force that is felt internally throughout the member, and so there are no bending moments or shear forces inside the member. So we need to find the reactions here at A and B, and then use the method of joints to find the internal force of each member. So now let's write our givens and finds. Other than this diagram, we're only given C and P, and then we want to find our reactions and the member forces. Alright, so for the reaction forces, I'm going to use R to symbolize reaction, and we have them at A in the X direction, and we have another one at A in the Y direction. And then at our point B, we see a different symbol. It's a triangle with wheels, and since it has wheels in the horizontal direction, it will not provide support in that direction, but it will provide support in the vertical direction. So we will have a support reaction at B in the Y direction, but not in the X. And then for the member forces, I'm going to use F, and use the pattern is acting between A and C, and we have 5 of those. All right, and once we finish our given and finds, we draw a single line to separate the problem from the solution. All right, so next we're going to be working on finding the support reactions, and to help with that, we will draw a free body diagram to kind of simplify our structure and focus on the forces instead of the structure itself. Alright, so when we have our coordinate axes, we need to label them as X and Y, and then I'm going to go ahead and draw all the points as well as the forces acting on them. Alright, and now let's talk about the distance between each of these points. So we are given the distance here as C over 2, and the same with here. And we also need to know where C is located relative to the other points. So we need to know this distance. And this part is important because we'll be using our summation of moments equation, and so we need to know the distance of each force from whatever point we choose to take our moments about. And then we also need this distance right here. And so if we look at our structure over here, we can see that this member is labeled as B. And so I am going to call this distance between A and C B. And so I'm going to move this up here. This distance I can call Bx, and this one as By. Alright, so there's a free body diagram. And let's think about what we should do first. So we have three unknowns. All the forces with an R are reaction forces. Those are our unknowns. And we have three unknowns, and we have three equations we can use. So there's the summation of forces in the x direction as well as in the y direction. And then our third one is the summation of moments about a point. And if we look at our unknowns, we see that there's only one that is in the x direction. So let's start with our summation of forces in the x direction, so we can solve that one first. And we need to choose a direction as positive. Usually just choose the direction of the x-axis. And since this structure is static, the summation of forces is equal to 0. Now we go through all of our forces and add them up, and the sign depends on its direction relative to what we chose as positive. So first we have our support reaction in the x direction, and it's in the same direction as positive, so we keep it positive. And then we have this force right here, this 2p, and it is also positive. And finally, we have this 2p right here, which is acting in the opposite direction, so we subtract it. All right, so looking at this, we can see that these two cancel out, and we are left with Rax is equal to 0. And if we had kind of looked at this free body diagram, we could have seen that those canceled out, and so this would have to be 0. Sometimes it makes it easier to just write it out and you don't have to think too hard. And this is one of our final answers, so we double underline it and draw an arrow from the margin and label it with the variable. All right, so now we have our two vertical support reactions. And we have two equations left. If we start with summation of forces in the y direction next, we will have two unknowns and won't be able to solve any of them directly. We would have to use it simultaneously with the moments equation. But if we start with the moments equation, we can take our moments about a point that has one of the reactions. So if we do the moments about point A, we won't have to worry about these forces acting at point A, and we will only have one unknown. So let's do that. Now our summation of moments about point A, and we're going to choose the counterclockwise direction to be positive. And our structure is not spinning, so we are going to set this equal to 0. And now we need all of our moments. And we see, so a moment is the force times its perpendicular distance to a point. So the reasons we don't take these two forces into account is because their perpendicular distance is 0, and so they don't have a moment. And similarly, this force right here, the 2p, acting at point D, its line of action goes through point A, which means that its perpendicular distance is also 0. But so with these other forces, like this P right here has a distance of c over 2, and these forces at C have our distances that we actually still need to find, bx and by. And so we actually need to find those values before we are able to do our moments equation. All right, we can go ahead and add this angle here, theta A, which we are given. And so, as you might be able to guess, if we know the length of this line here, we can use trigonometry and this angle to find our bx and by. So how do we find the length of member B? Well, let's go ahead and consider the entire structure as one triangle. So I'm going to go ahead and draw that. And so we have point A, point B, and point C. And we are given all of these angles. This is actually point B and point C. All right, and we know that this side length is C, 8 feet. I'm going to write in these angles here. All right, and this is the side length we are trying to find. So we have all of the angles and one side. And if you remember, we have two tools that we could use. There's the law of cosines as well as the law of sines. The law of cosines involves all three sides and one angle. And we only have one side, so we would have two unknowns if we tried to use that one. But the law of sines involves two angles and two sides. And so if we use that one, we will only have one unknown. So let's use the law of sines. So the law of sines tells us that the length of one side divided by the angle of the opposite corner right? So the length of this side right here divided by the sine of this angle is equal to the length of any other side divided by the sine of its opposite corner. And so since we know the length of side C, we're going to use that one and divide by the sine of its opposite corner, or the angle of its opposite corner, which is theta C. And you can see B is the only unknown here, so we can rearrange to find it. And when we plug this into our calculator, we get 5.22 feet. And this is an intermediate answer, so we give it a single underline. And now that we know B, we can find Bx, which following we can use our simple trig knowledge to find that. So Bx is going to be the length of B times the cosine of this angle. And it is 2.61 feet. And then we'll find By, which is the same but sine of the angle. And this one is 4.52 feet. All right. So now we can find our summation of moments. All right, so let's look at our free body diagram. And we can see that this force and this force, as well as this one, all have their line of action going through point A, so they will not create a moment about it. But we have these two forces here, as well as this one and the reaction at B. So we have 4 moments that we need to take into account. And we chose counterclockwise to be our positive direction. And so when we are summing them, any force that creates a moment in that direction will be positive, and any in the opposite direction will be negative. So these two forces here are both going clockwise around point A, and so they will be negative in our equation. Whereas this force at D and the reaction at B are going in the counterclockwise direction, so they will be positive. All right, so here is our equation. We have each force multiplied by its perpendicular distance to point A. And now we can rearrange to find RBY. And this is equal to 19.1 kips. And this is one of our final answers. All right, and finally we have our support reaction at A in the y direction that we need to find. And we have one final equation, which is the summation of forces in the y direction. We're going to choose up to be positive, and it's static, so we set it equal to 0. All right, so we have 4 forces acting in the y direction, 1 at each point. And if they're pointing up, they'll be positive, and this one, which is pointing down, will be subtracted. And then we see that these two cancel out, and we are left with RAY is equal to negative RBY, which is negative 19.1 kips. And that is our last support reaction. And now we need to find our member forces. So our problem statement says to use the method of joints. And what this means is at each joint, or at each point, we're going to create a free body diagram and balance all of the forces. So in addition to our reaction forces, as well as our externally applied forces, we're going to have the forces from the members acting at that point. So let's start with point A. I'm going to create a free body diagram. And point A has two reaction forces acting on it, right? So in the y direction and the x direction, and then we have the member forces. And which direction should we draw the member forces? Well, if you remember, the convention for internal forces is that tensile forces are positive, so the tension is pulling on the member, pulling it out, stretching it. But that is internally. So the member is being stretched, but it creates an opposite reaction on the point. When the member is being pulled, it is also pulling the point towards itself. So we will draw our member forces as going away from the point. And this will follow the convention so that if we get a positive answer, we know our force is in tension, and if it's negative, we know it's compression. And we're also given this angle here, which is theta A, which is equal to 60 degrees. And it's also a good idea to define our coordinate axes. So we have x and y, and that is our free body diagram. So since all of our forces are acting at a single point, we cannot use summation of moments because none of them create a moment at this point. But we still have our two equations, summation of forces in the x direction and in the y direction. So let's think about which one we should do first. If we do summation of forces in the x direction, we will have two unknowns. Both of our member forces have components in the x direction. But if we do summation of forces in the y direction first, you can see this one does not have a component, so it'll be left out. But this one does, and we can find it directly because we will only have one unknown. So let's go ahead and do our summation of forces in the y direction. Alright, so we have our reaction force at A in the vertical direction, and it's in the same direction as that we defined as positive. And we also have our member force AC, which has a component in the y direction. And they are both in the positive direction. And for the member force, we need to find the component that's vertical, so we multiply by sine of theta A. And then we rearrange to find FAC. And this is equal to 22.1 kips. Alright, and now we need to find FAD, so we will do our summation of forces in the x direction now that there is only one unknown in that direction. And so we have our reaction force as well as our FAD and the component of FAC that is in the x direction. So you multiply by the cosine of the angle. And if you remember, this reaction force was actually 0, so we can leave that out. So we have FAD is equal to negative FAC in the x direction. And so this is equal to negative 11.1 kips. All right, so now we need to move on to point B and draw a free body diagram for that as well. All right, so at point B, we have one reaction force and two member forces. And again, we'll draw the member forces as pointing away from the point. And we are given this angle. All right. So just like with point A, we have one force that is horizontal and one that is at an angle. So we're going to start with our summation of forces in the y direction again, so that we don't have to take into account one of our unknowns. And to find the component in the y direction, we multiply by the sine of the angle. And then we rearrange to get our force. And this is equal to negative 29.7 kips. All right, and finally we do our summation of forces in the x direction to find FBD. And FBD is, as well as FBC, are acting in the negative x direction. So we will subtract both of them. And for FBC, multiply by the cosine of the angle to get the x component. And then we rearrange for FBD. And FBC is negative, and since we're multiplying by a negative, it actually becomes positive 29.7 kips. and this is equal to 22.5 kips. This is actually 22.8 kips. All right, so we have 4 of our 5 member forces. The only one that's left is this middle one, which means that we could find it by looking at either point D or point C. So if we do it at point C, we notice that we have 3 member forces and they are all at weird angles. But at point D, only one of them is at an angle while the other ones are aligned horizontally and the applied forces are horizontal and vertical. So D should be simpler to solve. However, we will need this angle right here to be able to find our forces, our member forces X and Y components. I'm going to call this angle theta D. And so we will need to figure out what that angle is. So to do this, we can consider this triangle right here. And let's go ahead and draw that. So this triangle is between point A, C, and D. And we know we know one of these angles. We're trying to find the other one. And we know that this side length is C over 2, and this is B. And we actually already know the height of this triangle when we found BY, and the side length from here to A, which is BX. So we can find this angle by using our trigonometry. So if you remember, the tangent of an angle is equal to its slope, or in other words, the height divided by the distance. So if you remember the rise over run or opposite over adjacent, those are all different ways of remembering it. So basically we need this side length divided by this side length. So this right here is going to be the whole thing minus our bx. So c over 2 minus bx. So now we have our side lengths, and we know that the tangent of theta d, which is what we're trying to find, is equal to our opposite over adjacent, so by over c over 2 minus bx. Then we rearrange to find the angle. Finally, we get an angle of 72.9 degrees. All right, now let's do our free body diagram for point D, now that we have enough information. We could have also started with the free body diagram and found that we didn't have enough information. Then we'd go back and get the angle so that we could solve it. All right, so D has a lot of forces. We have our applied forces acting on D, as well as 3 member forces, which again we will show as pointing away from point D. And we found this angle, which is theta d. And the only unknown we have is FCD. And so we could use either the summation of forces in the x direction or the y direction, since it has components in both. But if we do the summation in the y direction, we could ignore all three of these horizontal forces. So let's do that one. And we need the y component of our member force, so we multiply by sine of theta d. And then we rearrange. This is equal to negative 20.9 kips. And that is the last force that we need to find. So we're done, and we draw a double underline under our work.